Hello and welcome to Vodcast 16.3. In this vodcast, I will overview stellar evolution. The ultimate reason that we have stars is the force of gravity. The gravitational force has a way of clumping things together, and star formation would not be possible if it weren't for the gravitational force. But inside of every star, there are two forces battling one another. The force of gravity wants to pull the star inward, but the stars are producing thermal energy in their cores, and as a result, there's a heat pressure directed outward. Recall that a star spends 90% of its lifetime in the main sequence stage, and when a star exists as a main sequence star, these two forces are balanced. The heat pressure produced at the center of stars is a product of nuclear fusion. When stars form, they're made predominantly of hydrogen gas, and under extremely intense pressure and extremely high temperatures, a hydrogen atom can fuse with another hydrogen atom to form helium. And when that process occurs, Einstein's E equals mc squared equation tells us that there will be a huge amount of energy produced. At this point, I'm going to overview stellar evolution from birth to death. Star birth takes place in a dark, cool interstellar cloud known as a nebula. And a good working definition for a nebula is an interstellar clump of matter rich in gas and dust that serves as the birthplace for stars. Now over time, the force of gravity is going to contract that nebula. And as that occurs over a long period of time, the temperature inside the nebula will rise. Eventually, a protostar will form. You're going to see the picture on this slide pop up over and over throughout this vodcast, and it's an extremely important picture. What you see is a Hertzsprung-Russell diagram that overviews the stellar evolution of a star from birth to death. In stage 1 we have a nebula, and the temperature of that nebula is relatively cool, and its absolute magnitude is pretty close to 0. But when a nebula forms a protostar, we see an increase in surface temperature and a very slight decrease in absolute magnitude. During the protostar stage, a collapsing cloud of gas and dust is on its way to becoming a star. The continued gravitational contraction causes motion that emits long-wave red light. Now let's talk about the transition from protostar to main sequence star. As the protostar continues to contract and heat, the core of the star will reach 10 million kelvins. And once that core gets hot enough, hydrogen nuclei will begin to fuse. More specifically, a hydrogen atom can be squeezed together with another hydrogen atom to form helium. When that process occurs, the star will begin to produce huge amounts of energy. And once hydrogen fusion begins, we officially have a main sequence star. Specifically, when a star becomes a stable main sequence star, energy will be released and outward pressure will be balanced by gravity. I'd like to stress once more that when we look at the big picture for stellar evolution, stars spend 90% of their lives in the main sequence stage. If we take a look at the Hertzsprung-Russell picture that overviews stellar evolution, when we transition from protostar stage to main sequence stage, we see a pretty substantial increase in surface temperature and a slight decrease in absolute magnitude. It's very important to note at this point that stars age at different rates. Massive stars will use up their fuel much faster than smaller stars. And due to that fact, massive stars will exist for only a few million years. I know it sounds weird, but I think of massive stars as Hollywood celebrities. They often live big, they die young, and when they die, they often die very dramatic deaths. And keep in mind, it's the most massive stars that will go supernova to produce black holes or neutron stars. As previously mentioned, smaller stars will use their fuel more slowly, and they can exist for hundreds of billions of years. So what happens to stars after the main sequence stage? Well, at this point, the end is near. The next stage of stellar evolution is the red giant stage. And it's during this stage that a helium-rich core is produced when all of a star's hydrogen-rich interior has been consumed. Stars want to fuse hydrogen into helium, but when there's no more hydrogen left, the hydrogen burning starts to work its way outward. As the core runs out of hydrogen and starts to fuse heavier elements, the star's outer envelope will expand. The surface of the star will cool and become red in color. A long time from now, our sun will go through this process. And when it does, it will expand to a point that it actually eats Earth. In other words, it will expand out past our orbit where Earth will be inside of the Sun. Don't worry, you and I will be long dead when this happens. But as the star approaches its final death twitches, the core will collapse as helium converts to carbon. And it should be noted that the heaviest element a star can produce through nuclear fusion is iron. During this red giant stage, the star can become a little bit unstable. Thermal energy is pushing outward and gravity is pulling inward. But when the hydrogen burning starts to migrate outward and the star begins to fuse heavier elements, thermal energy starts to win a little bit. That's what causes the star to expand. But gravity isn't going down easy in this fight. And in variable stars, you'll see expansion and contraction alternate. More specifically, the star won't reach equilibrium in this stage. Just as is the case with living organisms, the final stage in stellar evolution is death. And although this serves as the conclusion of this vodcast, in the next 2 vodcasts I will overview the death of low mass stars, intermediate mass stars, and high mass stars.